Welcome to Digital 6 Computers. It is assumed at this point you have a solid understanding of the logic circuits used in digital circuitry, Boolean algebra, memory devices, temporary storage devices like registers, math circuits, and numbering systems. You will see that electronic digital computers consist of three main subsystems or modules. These are the I/O or input-output module, the CPU or central processing unit, and the memory module. Since the CPU is the heart of the computer, we will begin with this section first. The internal structure of the CPU will vary widely among various computers. In the following portion of this video, we will describe a single central processing unit of a microcomputer. As you can see, it consists of an ALU or arithmetic logic unit, several registers, and a control section. The number of lines used to interconnect the registers and the ALU is determined by the word length. The word length is the maximum number of bits that the arithmetic logic unit can process in parallel. The word length in present-day microcomputers will vary between 4 to 16 bits, while full-size computers will commonly range from 12 to 64 bits. The ALU is the thinking part of the computer. The basic structure of the arithmetic logic unit can be divided into 4 sections. First, there is the arithmetic section, which performs the addition and subtraction process of the CPU. The arithmetic section is capable of adding or subtracting 2 different words at a time. The arithmetic section can also multiply or divide by using the successive addition or successive subtraction process. For more information on how this process works, review the UCanDo video, Digital 1. There is also a logic section contained within the ALU subsystem. The logic section performs the AND, OR, and exclusive OR and comparison functions of the CPU. The ALU also has 1 or more registers at its disposal. These registers are normally referred to as accumulators. After the arithmetic section or logic section has processed the data, the result or new data will be stored in the accumulator. The 4th section of the ALU contains the control circuits used to control the timing and sequence of the other 3 sections. It was mentioned earlier that the CPU also contained a control module. The control module may be thought of as being the electronic nerve center of the CPU. The control section is responsible for a number of functions. First, it must fetch the program instruction codes from the main program memory. It then interprets the instruction code for the operation requested. Once the instruction code has been interpreted, it executes the instruction. The control subsystem directs every activity which takes place within the computer. The control unit also makes use of a number of registers for temporary storage of data. One such register is the instruction register. The instruction register will fetch the program instruction code from the program memory. Next, the code is decoded by the instruction decoder, and then it is sent to the CPU timing and control section. The timing and control section then controls the memory and input-output functions of the computer. Once the control module completes one set of instructions, it fetches the next set of instructions and performs the process once again. The control section also monitors the input-output section at all times. You have also seen that the central processing unit contains a register section. The CPU contains several registers that are often called data registers, working registers, or simply scratchpad memories. The register section is used to provide storage for the data being operated on by the arithmetic logic unit. So far, you have seen that the CPU, or central processing unit, contains three basic sections. These were the registers, arithmetic logic unit, and the control section. You have also learned the basic function of each of these sections. Even though the CPU may seem quite easy to understand, it is a very complex maze of solid-state devices and gates. Therefore, we will take a minute to review some of this important material just discussed. A basic computer will contain three subsystems or modules. These are the CPU, I/O or input-output, and memory. The internal structure of the CPU will also contain three primary sections. These are the ALU, or arithmetic logic unit, a control section, and several registers. The ALU may be thought of as the thinking part of the computer. The ALU will contain a logic section, a control section, an arithmetic section, and some registers. The logic section performs the AND, OR, exclusive OR, and comparison functions of the CPU. The control section performs the function of timing and control of the sequence for the other three sections. The arithmetic section is used to add, subtract, multiply, and divide the data being fed into it. The control module contained within the CPU may be thought of as being the electronic nerve center of the central processing unit. Its function is to fetch the instruction code, interpret the code, then execute the instruction. The control module directs every activity which takes place within the computer. The CPU also contains several registers that are used to provide temporary storage for the data being processed. This concludes review number 1. Next, we will examine the I/O, or input-output module of the computer system. The input-output module is responsible for the transfer of data and control signals between the central processing unit and all supporting circuits outside the CPU. To better understand how the input-output section of the computer functions, we will examine this simplified block diagram of an I/O section. As you can see, it consists of 4 primary blocks. The input-output register provides temporary storage during the transmission of information between the central processing unit and the I/O section. Sections of the input or output devices is performed by the input-output multiplexers. The output storage buffers provide temporary storage for the data produced by the output multiplexer circuit. This data is then transferred to the output peripheral devices. The information sent to the peripheral devices will contain function codes which identify the task of the selected device as well as the data being transferred. It is important to note that the computer program controls the peripheral equipment. This is due to the fact that the computer instruction codes inform the peripheral devices of the type of operation to perform. The computer instructions also specify the memory areas for input and output data. The input-output section does not accept data from peripheral equipment or send data to peripheral equipment unless memory areas for the data have been specified by the computer program. Here you see a typical input-output cable configuration for a peripheral device. This device could be a keyboard, printer, mouse, hard drive, floppy drive, tape reader, or any device which operates through the control of the computer. The input request line carries a control signal which accompanies each input data word sent to the computer. This control signal informs the computer that an input data word is on the data lines. The external interrupt request line carries an interrupt control signal to the computer which informs the computer that an interrupt code is present on the data lines. The input acknowledge line carries a control signal from the computer to the peripheral device to acknowledge that the computer has accepted the input data word or interrupt code that was present on the input data lines. The data lines carry the interrupt codes and input data words to the computer. The output request line carries a control signal which indicated that the peripheral device is ready to accept an output data word from the computer. The output acknowledge line carries a control signal which accompanies each output data word sent to the peripheral device. This signal informs the peripheral device that an output word is on the data lines. The external function request line is a control signal which indicates that the peripheral device is ready to accept a function word. The external function acknowledge line carries a control signal which accompanies each function code word sent to the peripheral device from the computer. It informs the device that a function word is on the data lines. The data lines carry the output data words and external function words to the peripheral device. Now, let's consider the operation of how a peripheral device and the computer communicate. We will begin with the peripheral to computer communication first. When the peripheral device requests the computer to accept information, it will send a control signal through the external input request line to the computer. It also places an interrupt code on the data lines. When the computer acknowledges the external input request line, it will read the interrupt code which is present on the data lines. After the computer has processed the interrupt code, it will send a control signal through the input acknowledge line to the peripheral device to inform the device that the computer is awaiting further data. Next, the peripheral device sends another control signal to the computer via the input request line. The peripheral device also places the data to be transferred onto the data lines. After the computer acknowledges the input request signal, it reads the data from the data lines. Once the computer has read the information from the data lines, it sends another control signal through the input acknowledge line to inform the device that the data has been accepted. Now let's see what happens when the computer needs to communicate with the peripheral device. When the computer needs the peripheral device to accept data, it must first force the peripheral device to acknowledge that it is being requested. This is accomplished by sending a control signal through the external function acknowledge line to the device. The computer also places a function code word on the data lines. After the peripheral device sees the computer's command, it sends a control signal through the external function request line which informs the computer that it is ready to accept the function code word. Next, the peripheral device reads the function code word and prepares the device for the next command. The function code word will specify the type of operation the device is to perform. After the function code word has been processed by the peripheral device, the device will send a control signal to the computer through the output request line, informing the computer that it is ready to accept the output data word. After the computer reads the request from the peripheral device, it allows the data to transfer into the device. The computer also sends a control signal through the output acknowledge line to inform the device that the output data word is on the data lines. As you have seen, the processor and peripheral devices are able to communicate through a series of control signals placed on the various control lines. After the requests are honored, each device will perform its function. However, these peripheral devices send their messages to the processor at irregular intervals with requests for service. It is typical for more than one peripheral device to send a request for service at the same time. Therefore, a circuit is required to determine which device should have priority and be surfaced first. Here you see a priority encoder integrated circuit, which is designed to establish the priority among simultaneous requests for service. The purpose of a priority encoder is to generate a binary address for the active input with the highest priority. As you may have noticed, this is an 8-bit priority encoder IC. The inputs are labeled D0 through D7. There are also 3 outputs, which are labeled Q0, Q1, and Q2. The Enable In, Enable Out, and Group Select are the control pins on the device. Since the priority encoder is designed with an inherent priority system, it will depend on which request lines go to a particular input, which determine the priority of the request signal. Input pin D7 has the highest priority. Therefore, as long as D7 is held high, the remaining inputs will be ignored. If input pin D7 is low, then the next highest priority will go to input pin D6, and so on. We will now pause for a short review of the most recently discussed material. The input-output module is responsible for the transfer of data and control signals between the central processing unit and all supporting circuits outside the CPU. The input-output section consists of 4 primary blocks. There are the I/O register, the input multiplexer, the output multiplexer, and the output storage buffer. The input-output register provides temporary storage during the transmission of information between the CPU and the I/O section. Selection of the input or output device is performed by the input and/or output multiplexers. The output storage buffer provides temporary storage for the data produced by the output multiplexer circuit. Since it is typical for more than one peripheral device to send a request for service at the same time, a circuit is required to determine which device should have priority and be serviced first. This is accomplished through the use of a priority encoder circuit. This concludes review number 2. Next, we will examine a typical I/O integrated circuit. The MC6821 is a typical input-output chip designed by Motorola to operate with the 6800 family of MPUs. This IC may be found operating with the 6800 8-bit computer or with the 68000 16-bit computer. The 6821 is a peripheral interface adapter, or PIA for short, which is constructed using NMOS technology. Data bus lines D0 through D7 allow the microprocessing unit to write data to or read data from the 6821 as if it were a memory location. Pins PA0 to PA7 and PB0 to PB7 are used to interface all the peripheral devices except for the video display. The video display has its own I/O device. The IC itself is addressed with 3 bits. These are the chip select pins CS0, CS1, and CS2. When the IC is selected, inputs chip select 0 and chip select 1 are brought high, while input control pin chip select 2 is held low. The inputs labeled RS0 and RS1 are the 2 address lines used for internal registers within the IC. Through the use of the 3 chip select inputs and the 2 register select inputs, one of 4 locations in the PIA can be accessed. The PIA is typically in a high impedance state until it is addressed. When data is being transferred within the PIA, the enable input pin is brought high. The enable input is controlled by the MPU. Pin 21 is the read-write control input. This signal is generated by the MPU and is used to control the direction of the data flow on the data bus lines. When the read-write line is low, the data is transferred from the MPU to the PIA address. And when the read-write line is made high, it sets up the PIA for transferring data from the PIA to the MPU. It was mentioned earlier that the PIA has two 8-bit input-output registers. These were labeled PA0 to PA7 and PB0 to PB7. Inside the PIA, these input-outputs connect to 4 addressable registers. As you can see, there are 2 identical strings of registers, and each string connects to the data bus line registers. The peripheral data register and the data direction register are connected internally bit by bit. Since these registers work together, they are considered as being one location on the IC. Therefore, both are assigned one address. As you can see, one set is addressed FF00 and the other set is addressed FF03. The data direction register performs one primary function. It decides if the peripheral data register is to input information or output information. This is ultimately controlled through bit 2 of the control register. If the control register receives a high at bit 2, then the peripheral data register is made an output. If, on the other hand, the control register receives a low at bit 2, then the peripheral data register is made an input. Here is a simple example of how these registers work. In our example, we will use peripheral port A. Keep in mind that port B works the same way. When the processor first turns on, bit 2 in the control register will be low. The processor then writes to the data direction register and gives the input or output assignments. Once this is done, the processor will force bit 2 in the control register high. This allows the instructions contained in the peripheral data register to output to the peripheral device. Pins CA1 and CA2 are 2 more of the control pins used on this IC. They work together to perform what is known as a handshake. Here is an example of how the handshake works. The handshake begins when the peripheral device places a high on pin CA1 of the PIA. This information is then transferred through the data bus to the MPU. Basically, the peripheral device is informing the processor unit that it has some data to send to it for further processing. The processor acknowledges the peripheral's request and sends a high signal through the data bus to the PIA, then through pin CA2 to the peripheral device to tell it that it is ready to receive the data. Next, the peripheral device sends the data through the PIA to the processor. Control pin CA2 will remain high during this time period. After the data transfer is completed, the processor will force control line CA2 low again to indicate that the MPU is ready for the next batch of information. As you can see, the handshake is nothing more than messages sent back and forth between the devices in the forms of highs and lows, which indicate when to transmit data and then to acknowledge the receipt of the data. Control pins CB1 and CB2 are used in the handshake process for the peripheral device attached to inputs PB0 through PB7. Even though the PIA, or peripheral interface adapter device, is capable of both serial and parallel functions, it is usually thought of as being purely parallel. Before continuing the discussion on I/O circuits, we will pause for a short review of the material just discussed. The 6821 is a peripheral interface adapter, or PIA for short. It is constructed using NMOS technology. The microprocessor can read data from or write data to the 6821 through the data bus lines D0 through D7. The 6821 also has two peripheral ports. Port A uses pins PA0 through PA7, and Port B uses pins PB0 through PB7. This IC may be addressed through three chip select pins, CS0, CS1, and CS2. The inputs and outputs of this device are typically held at a high impedance state. Only when the chip is addressed and a high is placed on the enable input pin does the CPU actually see this device. The peripherals connected to the 6821 are accessed by the microprocessor through a procedure referred to as a handshake. The handshake is nothing more than a series of control pulses being exchanged between the peripheral devices and the CPU. These pulses are used to indicate when to transmit the data and then to acknowledge the receipt of the data. This concludes review number 3. Next, we will examine a typical serial input-output device. Parallel ports are much faster and therefore more efficient than serial ports due to the fact 8 bits or more of information may be transmitted at one time. However, there are situations in which the cost of transferring information in parallel becomes a deciding factor. For example, if you were using a phone modem to communicate with another PC user, a parallel modem would require a minimum of 8 separate phone lines to transfer just the data. More lines would be required for the control signals. As you can see, this would become a very costly form of communication. In contrast, a serial communications link requires only one line to transfer the same information. As was mentioned earlier, the serial ports are slower than parallel ports, simply because the data can only be transmitted 1 bit at a time. Another difference is the bit length of the transmitted data will be longer with the serial device due to the fact certain format bits, like the start bit, parity bit, and stop bits must be added to the data. These format bits are used to control the device for read and write operations. Here you see a universal asynchronous receiver transmitter integrated circuit. The UART is a special digital IC which contains separate data transmitter and receiver sections. The transmitter section of this IC will accept parallel data from the MPU, then transfer the data in serial form to the peripheral device. The receiver section, on the other hand, will accept the input data in serial form, then convert it to parallel data for processing by the microprocessing unit. Basically, the UART makes the task of receiving and transmitting data in serial form easier for the processor. Most universal asynchronous receiver transmitter ICs are capable of being programmed by the end user to determine the word length, baud rate, parity type, even or odd, parity inhibit, and the stop bit length. The UART also provides 6 status flags. These are transmission complete, buffer register transfer complete, received data, parity error, framing error, and overrun error. We will briefly examine the function of each pin on this IC. Pin 1 is labeled VCC. It will connect to the positive 5-volt side of the DC power source. Pin 2 is labeled VEE. It is commonly connected to the negative 12-volt power supply. Pin 3 is labeled GND. It, of course, is connected to the ground plane. Pin 4 is labeled RRD. It is the receiver register disconnect input. A high on this pin places the receiver data output pins, which connect to the MPU bus line, in a high impedance state. A low input, on the other hand, allows the receiver data output pins to connect to the data bus. Pins 5 through 12, which are labeled RB1 to RB8, are the receiver data output lines. The data received from the serial input pin is converted to parallel form, then transferred through pins 5 through 12 to the microprocessor. Pin 5 is the least significant bit, and pin 12 is the most significant bit. Pin 13, which is labeled PE, is used to indicate a parity error. A high on this pin indicates that the parity of the received data does not match the parity programmed at pin 39. Pin 14 is labeled FE for framing error. A high at this output indicates that no valid stop bits were received. Pin 15 is labeled OE for overrun error. A high on this pin indicates an overrun condition. This condition may occur when the data received input is not reset before the next character was received by the internal receiver holding register. Pin 16 is labeled SFD for status flag disconnect. When pin 16 is brought high, it places pins 13, 14, 15, 19, and 22 in a high impedance state. This allows the status flags from several universal asynchronous receiver transmitters to be connected to the same communication bus. Pin 17 is labeled RRC. This is the receiver clock input pin. The clocking frequency on this pin should be 16 times the desired baud rate. Pin 18 is labeled DRR. It is the data receive reset. When this pin is brought low, it resets the data received flag. Pin 19 is labeled DR. It is the data received flag input. A high on this pin indicates that the data was received and is in the receiver holding register. Pin 20 is labeled RI. It is the receiver serial input. All serial input data is applied at this input. Pin 20 is held high when no data is being received. Pin 21 is labeled MR and is the master reset. A short pulse applied to this pin will reset the registers and flags in both the receiver and transmitter sections. Pins 22, 24, and 25 will be set high while all other registers and flags will be set low. Pin 22 is labeled THRE. This is the transmitter holding register empty pin. A high on this pin indicates that the data in the transmitter input buffer has been transferred to the transmitter register. This allows new data to be loaded. Pin 23 is labeled THRL. It is the transmitter holding register load pin. A low on this input allows the data being applied at inputs TB1 through TB8 to be entered into the transmitter holding register. A high on this pin then transfers the contents of the transmitter holding register to the transmit register. Pin 24 is labeled TRE. It is the transmit register empty pin. This pin will remain high until a transmission of data takes place, at which point pin TRE drops low. Pin 25 is labeled TRO. It is the transmitter output for the serial data. All data and control bits are output on this pin. The TRO remains high when no transmission is taking place. Pins 26, 27, 28, 29, 30, 31, 32, and 33 are the data inputs from the microprocessor. Pin 26 is the least significant bit, and pin 33 is the most significant bit of the input data. These pins are labeled TB1 through TB8. Pin 34 is the control register load pin and is labeled CRL. This pin is generally wired permanently high. However, it can also be strobed with a short positive going pulse if it is desired to change certain parameters of the IC. When this pin is high, the programmed instructions on pins 35, 36, 37, 38, and 39 are loaded into the internal control register. Pin 35 is labeled PI. It is the parity inhibit pin. A high on this pin will disable the parity generation verification function of the IC and force pin 13 to a logic low condition. Pin 36 is labeled SBS. It is the stop bit select pin. The UART can be programmed for the number of stop bits to be added to the data word output. A high on this pin will cause the IC to generate 2 stop bits if the data word length is 6, 7, or 8 bits long. A low on this pin will cause the IC to generate only 1 stop bit. Pins 37 and 38 are the word length select pins. They are labeled WLS1 and WLS2. These pins are used to select the data bit length. Pin 39 is the even parity enable pin and is labeled EPE. When this pin is high, the IC checks for even parity, and when the pin is low, the IC checks for odd parity. Pin 40 is labeled TRC. It is the transmit clock input pin. The clocking frequency on this pin should be 16 times the desired baud rate. Generally, the transmitter and receiver sections are operated at the same baud rate. Therefore, you will normally find both clock pins, TRC and RRC, wired together and fed by a common clock circuit. As you can see, the universal asynchronous receiver transmitter integrated circuit communicates in parallel with the CPU and outputs or inputs data in serial form to the connected peripheral device. This classifies the UART as a serial I/O device, since the data is handled in serial form to and from the peripheral device. Here you see the typical data format for a UART device. Since the serial input or serial output is held at a high impedance state, they must be brought low to start the transmitting or receiving of data. Therefore, the first bit in the transmitted data will always be a low bit. The low start bit is then followed by the data contained in the data bit group. The next bit following the data information is the parity bit. If this bit is high, then even parity is used. If this bit is low, odd parity is used. The following one or two bits are the stop bit codes. The stop bits are used to tell the processor that the data is completed. The start bit, parity bit, and stop bits are used to replace the separate control lines which would be required in the typical parallel I/O configuration. Once the start bit swings low, the UART alerts the processor that the peripheral device has data to transfer. The processor then acknowledges the signal from the UART and allows the data to be transferred from the UART IC to the CPU. After the stop bits have been received, the processor continues with other operations. We will now pause for a short review of the most recently discussed material. Parallel communications are a much faster form of data communication. This is due to the fact data is transferred in parallel. However, when data must be transferred over long distances, serial communication methods are preferred. The Universal Asynchronous Receiver Transmitter IC is a common serial I/O device. It is capable of receiving and transmitting data information in serial form to connecting peripheral devices. The serial information received is converted into parallel information before it is directed to the processor. In the same respect, the processor sends parallel data to the I/O device, where it is converted into a serial format before it is transmitted to the peripheral device. The serial formatted data must contain certain control bits. These are the start bit, parity bit, and the stop bits. Other control bits may also be included. This concludes review number 4. Next, we will examine the video input-output system. The video display has become an important part of the computer system. This was brought about by the development of various video interface chips. Basically, video interface chips send the data from memory locations to the video display. Most monitors are nothing more than specially designed television receivers. Earlier video interface circuitry consisted of a character generator with latched inputs and a shift register at the output. The character generator was basically a ROM device which contained all the alphanumeric characters called the character font. We will begin by examining how this simple circuit worked. The typical computer system will have a portion of its RAM set aside to store the characters which will appear on the monitor screen. This section is referred to as the video RAM, and in earlier models, this section was typically 512 bytes. Now with larger modern computers, the demand for video RAM space has greatly increased. Since there were 512 bytes of RAM set aside for the video screen, the display was divided into 512 sections. The screen was divided into 32 horizontal sections, or columns, and 16 rows were displayed. Each section was able to display one alphanumeric character. As the keys on the keyboard were pressed, the characters were converted into a 7-bit format and stored in the video RAM in the sequence in which they were typed. Meanwhile, the display monitor would scan the screen with a 192 electron beam scan lines at a rate of approximately 60 times a second. On each line there would be 256 dots of energy, or pixels of light. Each bit or dot could be turned on or off according to the data being inputted. As you recall, the video RAM was fed through a latching device into the character generator. The character generator is nothing more than a ROM coding device. It receives the 7-bit formatted data and outputs 7 scan lines of 5 dots each per character. If you were to magnify a single character section, you would notice that each character could be illustrated in this 5x7 block by simply turning on or off each point of light within the designated area. Through the use of clocking signals for proper timing, the serial data is fed into the monitor's input circuitry, then scanned onto the faceplate of the screen. Basically, the data was used to control the electron gun contained in the cathode ray tube. In recent years, however, the latches, character generator, shift registers, and other support circuits have all been contained in a single IC package. The basic operation of these newer ICs is essentially the same as the earlier video interface circuits. However, they are much easier to service due to everything being contained in one dual inline package. Here you see a very popular video interface integrated circuit. This IC chip contains its own type of support latches and registers previously described. However, this device uses an 8x8 or 12x8 character font and is capable of generating a color screen as well as support circuitry for refreshing dynamic RAM chips and CPU clock timing. This input-output device transforms digital signals into complex video waveforms used by composite-type monitors. By now you should be familiar with many of the pins located on this device. Pins 1 through 7 and pin 39 are the data bus connections, which represent data bits 6 through 0 and data bit 7, respectively. These lines transfer data bidirectionally to and from the device. IRQ, labeled at pin 8, which you have previously learned is the interrupt request line output. When this line, normally held high, goes low, the device requires service from the CPU. The pin labeled LP at pin 9 is the light pen input. This input lets the user take an electronic type pen, which is basically a photoelectric switch, and draw on the screen of the monitor. The light of the monitor triggers the switch. The chip select, labeled CS, is located at pin 10. When this input, normally high, goes low, the device will be selected for read-write operations by the CPU's addressing. However, when pins 16 and 17 go low, this device ignores whatever logic condition is present at the chip select pin. Pin 11 is labeled RW. This is the familiar read-write pin, which is tied directly to the CPU. When this chip is selected, as previously mentioned, the read-write input pin, normally held high, determines the direction data will travel on the bidirectional data bus. That's pins 1 through 7 and pin 39. When pin 11 is high, the CPU will expect to read the device's addressed register. When pin 11 is pulled low by the CPU, data will be addressed to a register and written into the device. However, when pins 16 and 17 go low, the 6567 video interface device ignores whatever logic condition is present on this read-write pin. The next pin down, pin 12, is labeled BA. It is the bus available output. This normally high output is brought low when the device needs an extra clock pulse to access one of its internal registers or to access external RAM or ROM memory. When this device determines it does need the extra clock pulse, the BA pin is pulled low before the clock pulse on pin 17 goes back to high. Pin 13 is labeled VDD. It is simply a positive regulated 12-volt power supply to the chip. Pin 14 is labeled color. This pin supplies all the color information required by the composite monitor to reproduce various colors. Without the use of this pin, a monochrome or one-color display shows up on the screen. Pin 15 is labeled Lum Sync. It determines the luminance or brightness of the dots on the screen. Sync refers to the method of keeping the dots perfectly aligned with each other. Note both pins 14 and 15 are the only pins on the 6567 that are not digital. These output pins are analog. An oscilloscope must be used to read the complex waveforms being generated by these two pins. A digital logic probe just wouldn't reflect the true composition of both waveforms. The next pin down is pin 16. This pin is labeled AEC, which stands for Address Enable Control. This output line is used for actually placing the CPU and other chips not required by the video section in a high impedance state when the device needs the second clock pulse to operate. AEC goes low only after the bus available signal has been sent to the CPU and pin 17 has passed 3 high clock pulses. When AEC is normally high, the CPU operates as usual and the video interface may be addressed by the CPU. Pin 17, labeled REF-CLK, is the reference clock that generates a series of clock pulses, usually around 1 MHz, and is used by the CPU for timing throughout the entire computer system. When this pin is low, the CPU does not operate during this low pulse. This lets the 6567 video interface IC do its job, such as refreshing RAM and reading memory for video signal composition. When this pin is high, the CPU is in normal control of the system. However, if the 6567 needs an extra clock pulse to finish up, AEC will become low, putting the CPU into a high impedance state during its normal high pulse of operation. This allows the video chip to use the CPU's high pulse to control address and data lines normally controlled by the CPU. Pins 18 and 19 are used in conjunction with one another to refresh the dynamic RAM memory chips contained in the computer system. Pin 18 is labeled RAS. This stands for Row Address Strobe. Pin 19 is labeled CAS, which stands for Column Address Strobe. If you don't fully understand how or why dynamic RAM chips are refreshed, refer to Digital 5 of this UCanDo series for a proper understanding of memory devices. Pin number 20 is labeled VSS. This is the ground pin of the chip that goes to the 0 voltage potential. On the bottom right of the video interface IC is pin 21 labeled Color CLK. This is the color clock input pin that uses approximately 14 MHz pulse train as a reference for building the analog waveform coming out of pin 14 labeled color. The next pin up, pin 22, is labeled CLK-IN. This is the clock input pin, which is also referred to as the dot clock. This pin receives an approximate 8 MHz pulse used internally by the chip for its own timing and positioning of the electron beam. The pulse is also divided by 8 for output on pin 17, which in turn is used by the CPU for system clock reference. Pins 23 through 34 are all address lines. Let's first focus on pins 24 through 29, labeled A0, A8, A1, A9, A2, A10, A3, A11, A4, A12, and A5, A13. These individual pins are used in a method called multiplexing, which in this case is simply the organized sharing of pins. When the RAS signal on pin 18 goes low, the address bits A0, A1, A2, A3, A4, and A5 are placed on pins 24 through 29 respectively. And when the CS signal on pin 19 goes low, the address bits A8, A9, A10, A11, A12, and A13 are placed on pins 24 through 29 respectively. Addressing of the video interface by the CPU occurs when the address enable control pin is normally high and the chip select pin is low. This sets up bits A0 through A5 of pins 24 to 29 to be used for addressing all 47 of the chip's internal registers. Since there are only 47 internal registers in the device and 64 possible addressing combinations which can be present on pins 24 to 29, various combinations of internal registers can be addressed at one time, thus merging all corresponding register bits together to form one basic input or output. Pins 30 and 31, labeled A6 and A7, are two address lines used by the chip to simply address 2 kilobytes of memory. The output of these two pins represent a form of program counter that is used by an external addressing multiplexer circuit to select character ROM and video RAM data. Notice that all of the pins 24 through 31 output addresses onto address lines for accessing its own data, much like the CPU. We finally come to pins 23, 32, 33, and 34, which are labeled A11, A8, A9, and A10 respectively. These pins are normal address lines which have no special function but to simply receive signals from the CPU's address bus. Pins 35 through 38 are labeled D11, D10, D9, and D8. These 4 data lines coming from color RAM tell the video interface chip what color to make the characters that appear on the screen. The 4 data bits make it possible for the video chip to display up to 16 different character colors on the screen at one time. When the video interface addresses the dot patterns from video RAM or character ROM, color RAM also gets addressed at the same time. Pins 35 through 38 input data to provide color for the display screen. The last pin we have to cover is pin 40. Labeled VCC, this pin is simply the positive regulated 5-volt power supply to the chip. We will now pause for a final review of the most recently discussed material. The video RAM receives data from an input device such as a keyboard or telephone modem. The exact placement of data in video RAM represents the location in which it will appear on the face of the monitor's screen. The character generator, or character ROM, is programmed with the patterns of characters which get displayed on the screen. This is referred to as the character font. The character font for every letter is made up of a block of bits. The bit's logic state determines if a point of light will be scanned onto the face of the monitor. A point of light is also referred to as a dot or pixel. The video interface in any computer must continuously scan through video RAM so that the correct block of bits stored in character ROM may be indexed and displayed on the face of the monitor's screen. Otherwise, the dots or pixels of light formed by the electron beam scanning the face of the monitor screen would fade out so quickly an image would be almost imperceptible to the human eye. This concludes review number 5. If you have problems understanding any portion of this video, rewind and view as many times as necessary until you have a full understanding of the material presented. Since the central processing unit is the heart of any computer system, it becomes necessary that you know and understand how it works. Remember, the best jobs will go to those who are the best prepared. With the help of UCanDo videos, your knowledge and understanding of today's complex circuits will help make you a leader in troubleshooting tomorrow's electronic equipment.